Hello, welcome to Morin's Red Book Chapter 1 Solutions. We're going to start with 1.5 Problems, Section 1.2 Units and Dimensional Analysis. 1.1 Escape Velocity. As given below in Exercise 1.9, show that the escape velocity from the Earth is v equals square root 2gme over r up to numerical factors. You can use the fact that the form of Newton's gravitation force law implies that the acceleration and hence overall motion of the particle doesn't depend on its mass. Now let's look at the formula. We're given v equals the square root of 2gme over r. So, as it tells us, the v is equal to the escape velocity, the g is equal to the universal gravitational constant, the m is equal to the Earth's mass, and the r is equal to the distance between the object and the center of mass of the Earth, which in this case is the Earth's radius. So to more easily understand the numerical factors part, I think it's just easier to derive the v equals square root 2gm over r. So we'll just start out with the conservation of energy. So this just says that the initial energy is equal to the final energy. So now we can make the initial energy kinetic energy plus potential energy. So kinetic energy is 1/2 mv squared, and then the potential energy is negative m over r squared, capital M being the Earth and the lowercase m being the mass of the object. So now let's just look at this case for the final energy. So as it goes way out, the distance between the object and the center of the Earth tends to infinity. So that's why we can say that the potential energy is about 0. Furthermore, the velocity also becomes very, very small, about 0. So that's why we can say that the kinetic energy is also 0. So we approximate the final energy to be equal to 0. So then, if the final energy is equal to 0, and we already stated that the final energy is equal to the initial energy, then the initial energy also must be 0. So now we just write our equation for the initial energy and then set it equal to 0. Move the negative gm over r squared, cancel out the n's, and then move it around to just get the v alone. So that's how you derive the formula for the escape velocity. So now that we have that, let's try to do it with Morin's hint. So he said something about gravitational force, and that is equal to g m Earth times m over r squared. We also know that F is equal to ma. So now we can set the two F's equal to each other, cancel out the m object, and now you can really see how we're just taking out the object's mass, meaning that we're showing that it has no dependence. So now we have that a of r is, with a being the acceleration, is equal to g m Earth over r squared. Now we can see a key insight. The acceleration doesn't depend on the object's mass, so motion doesn't depend on it either. So now we can write this in terms of its dimensions, where L is going to be equal to the length, M is going to be equal to the mass, and then T is going to be equal to the time. So G is equal to L cubed over mt squared, ME is going to just equal to mass, and then R is going to be equal to L. So here what we're doing is we're writing it in terms of its exponents. We don't know the dependence yet, and that's the whole point of the numerical factor. We're just trying to find out its dependence, and we can do this through its dimensions. So we know that g to the power of a times me to the power of b times r to the power of c has to equal v. So now all we're going to do is we're just going to put them in their dimensions. So now we can isolate each dimension. So we have L equals 3a plus c. This is because just using the power rule, even for g, L cubed, now we also raise it to the power of a, so we can say that's just L3a. And now we know that velocity is equal to length over time, so we can know that that equals 1. So 3a plus c equals 1. Using similar steps, we know that for mass, b minus a, and that we need equal to 0. And then for time, it's negative 2a, and we need that equal to negative 1. So now we just have to solve it algebraically. So using the time, we have that a equals 1/2. And then from the math, we know that b equals a. So now we can just write b equals 1/2. And then now plugging the a into the L, we can find that c is equal to negative 1/2. So when putting them in, we have that v is about the square root of g me over r. Therefore, there is no dependence on the m object. Okay, let's move on to 1.2, mass in a tube. A tube of mass capital M and length L is free to swing around a pivot at one end. A mass of lowercase m is positioned inside the frictionless tube at this end. The tube is held horizontal and then released. See figure 1.5. Let n be the fraction of the tube that the mass has traversed by the time the tube becomes vertical. Does n depend on L? So the first key insight we have to take away from this is that n is just a fraction. That's how they defined it. And just like 1/2, 2/3, these are all dimensionless. Therefore, n is also dimensionless. So now we also have to look at its possible dependence. So it can be dependent on m, the length, the lowercase m, or the force. And in this, we know that the only force we have is the gravitational force. So we can set it equal to m to the power of a times L to the power of b times m to the power of c times g to the power of d is equal to no dimension. And with that, now we can set them to their dimensions. So all of them have their intuitive dimension except maybe g, which is, as you know, meters per second squared usually. So that's L over t squared. So for L, we have two cases. Either it depends on L or it doesn't. We can also think of this as either b equals 0 or b doesn't equal 0. In the case that it does depend on L, which means that b doesn't equal 0, we also have to make sure it follows a constraint that n has no dimension. This means that d also must not equal 0, so that it can cancel out b. However, you see that if d is not equal to 0, that means that there is also some t squared. However, there is no other dimension that can cancel out the t squared, so if n has no dimension, this means that d must equal 0. That also means that b must equal 0. Therefore, there is no dependence on L for n. We can see that there is possible dependence on uppercase m or lowercase m, as they could have their dimensions of mass cancel out for no dimension. However, we are definitely not certain which way it goes, or if there is even dependence. Question 3. Waves in a fluid. How does the speed of waves in a fluid depend on its density rho and bulk modulus beta, which has units of pressure, which is force per area? So first we know that speed is going to be equal to distance over time, so the dimensions are L over t. And we have given that it has dependence on rho, which is m over v, and b, which is force over area. So for rho, m is just m, and v, volume, is equal to L cubed. So now we have F over a. We can think of this as mass times acceleration. We know that mass is just m, and acceleration is L over t squared. And then we have area, which is just L squared. So we have that is mL over t squared over L squared, which is going to be equal to m over L t squared. So now we do the same thing as we did before. We first write it in terms of the just powers. So we have that the speed is equal to rho to the power of a times beta to the power of b. So L over t is equal to m over L cubed to the power of a times m over L t squared to the power of b. We just wrote them in its dimensions. So now we have L equals negative 3a minus b equals 1, m equals a plus b equals 0, t is equal to negative 2b, and that's equal to negative 1. So with the time one, we can just find that b is equal to 1/2, and then with the mass one, we can find that b is just equal to negative a, so then a is equal to negative 1/2. And we don't even need the length one because we only have two unknowns. So we know that the speed is proportional to the square root of beta over rho. Question 4. Vibrating star. Consider a vibrating star whose frequency nu depends on at most on its radius r, mass density rho, and Newton's gravitational constant g. How does nu depend on r, rho, and g? So we know frequency nu is equal to 1 over seconds, so 1 over t. And then we have possible dependence on r, which has dimension L, rho, which is m over v, so we know that has dimensions m over L cubed, and then we have g. You might not know this, but this one is equal to L cubed over m t squared. So now, again, let's just write it. Nu is equal to r to the power of a times rho to the power of b times g to the power of c. And now dimensions, 1 over t is equal to L to the power of a times m over L cubed to the power of b times L cubed over mt squared to the power of c. So let's write for our equations for length, mass, and time. So for length, a minus 3b plus 3c is equal to 0. Mass, m minus c is equal to 0. And then for time, negative 2c is equal to negative 1. So first with the time equation, we can just find that c equals 1/2, and then with the mass, a little rearranging, and we get that b equals c. So that means that b is also equal to 1/2. And then with the length, we know that negative 3b plus 3c is equal to 0, so we know that it is equal to 0. So it actually has no dependence on the radius. So that's how we know that nu is equal to the square root of rho times g. So last question, 1.5, damping. A particle with mass m and initial speed v is subject to a velocity-dependent damping force of the form b times b to the power of n. A. For n equals 0, 1, 2, and so on, determine how the stopping time depends on m, v, and b. For problem B, all we do is determine how the stopping distance depends on the same things for the same ends. So this is definitely the hardest question of the set. So first we can just write it. F of v is equal to b times v to the power of n. And we know that F equals ma from Newton's second law, so we'll just rewrite it. Ma is equal to b times v to the power of n. So we know that a is the derivative of the velocity with respect to time. So let's just write that. M equals dv over dt equals negative bv to the power of n. And we just added the negative sign because it's a damping force. So first let's just find out what the units of b are as we're performing dimensional analysis. So we found before that F is equal to n times L over t squared, and v is equal to L over t. And these are the only things that it is given it can depend on. So we have that b is equal to F over v to the power of n, and we just got this by rearranging our first equation. So now just plug in all the dimensions. So we have ml over t squared over L over t to the power of n. Keep in mind, you still have to keep n as a variable because you don't know what it is, and we're going to try to find a general solution first and then find cases for n later. So now we can write this as m times L times t to the negative 2 over L to the power of n times t to the power of negative n. And now we're going to do some rearranging with the idea of x to the power of a over x to the power of b is equal to x to the power of a minus b. So for final, we get b is equal to m times L to the power of 1 minus n times t to the power of n minus 2. As this is not a derivation, there are limitations. Keep that in mind for we can't find the constants and for other cases that we'll find out soon enough. So we're going to assume that the stopping time can be built from m, b, and v. This is one of the limitations of this dimensional analysis. We have to assume things. So we have that t is proportional to m to the power of a, b to the power of c, and v to the power of d. I didn't want to use b as an exponent because it kind of just makes it a little complicated. So we know that t has the dimensions of time. So now let's just rewrite all of them with dimensions. And for the m, we have a plus c equals 0. For the L, we have c times 1 minus n plus d equals 0. And then for t, we have c times n minus 2 minus d equals 1. So now I'm just going to show you all the steps. These are just systems of equations, so if you need to, just look over these. We get that. So then we end with the time is proportional to m over b times v to the power of 1 minus n. And now we can just find limiting cases. So if n is equal to 0, there's a constant damping magnitude, so it'll hit v equals 0 at a finite time. However, in all the other cases, if n is greater or equal to 1, it just gradually becomes weaker and weaker. So it never hits but just approaches 0, so technically there's an infinite stopping time. And for part B, it's asking about the distance, so we're going to do the exact same thing, but instead of the time dimension, we're going to set it equal to the length dimension. So we have m, mass, is equal to a plus c, which is equal to 0. Then we have c times n minus 2 minus d is equal to 0 this time. And then we have c times 1 minus n plus d is equal to 1. So now again, just solve the systems of equations, and this time we get that the distance x is proportional to m over b times v to the power of 2 minus n. So here we just use the same analysis that we used for part A, and we find that if n is less than 2, the distance is finite, and then we have that if n is greater than 2, we have the distance is infinite.